Okay, for the topic we'll be looking into, we have what is referred to as the gamma function. And the gamma function is an improper integral. And the symbol for gamma, at least for what will be present in both power series as well as Laplace transforms, okay, we have this symbol is in reference to gamma. And we had the input, if we let this be at x, we had that gamma of x is equal to the improper integral as t goes from 0 to infinity. And we have of t to the x minus 1 times e to the negative t dt. Now, we're going to be looking at translating what we have in the gamma function in terms of factorial notation. And just to start us off, okay, if we have the input x to be equal to 1, okay, so we have t to the 1 minus 1, that would be t to the 0, which would be 1. So for gamma of 1, okay, so you have the integral as t goes from 0 to infinity, and we have of e to the negative t dt. Applying limits, we have the limit as b goes to infinity. And this time we have t going from 0 to b. Again, we have of e to the negative t dt. And what we have with the antiderivative of e to the negative t dt, okay, this will be the negative of e to the negative t. Again, as t goes from 0 to b. So we have negative e to negative b. And what's going to become plus e to the 0 and for what we have, essentially, you have like negative e to the negative infinity, and so you have negative e raised to the negative of infinity. And for what we're going to have in this particular case, we're going to have a negative infinitesimal, and we have e to the 0, okay, that is going to be at 1. And so for what we are going to end up with for gamma of 1, okay, this is going to converge to 1. And we'll be looking at other values like gamma 2, gamma of 3, and reverting back to what we have with gamma of x. If I extend the input x, project on out to x plus 1, and we have with an improper integral, again we have going from 0 to infinity, and this time we're going to have t to the x plus 1 minus 1. So this will be of t to the x times e to the negative t dt. And here, once again, we have an improper integral. Now, for this particular item, if I look just for the antiderivative terms, and this is one where we'll be looking at integrating by parts. So for what we have in the general integral, okay, so I have t to the x times e to the negative t dt, and just taking what we have now, if I set u equal to t to the x, and taking the derivative with respect to t, so we have x times t, I have raised, okay, to the x minus 1 dt. And we have for dv, we have equal to e to the negative t dt. Antiderivative v, again we're going to have it the negative of e to the negative t. Applying what we have with the integration by parts, again you have u times v. So you have the negative of t to the x times e to the negative t. And we have minus a negative. And this will just translate out to plus. And we'll say we have x times the integral of t to the x minus 1 times e to the negative t dt. And in looking at what we have, applying what we have for the improper integral, so again, if I take the limit as b approaches infinity, so I have t going from 0 to b, and I have of t to the x times e to the negative t dt. And we had the limit as b approaches infinity, and just taking the antiderivative terms, we have negative t to the x times e to the negative t. Again, I have plus x times the integral of t to the x minus 1 times e to the negative t dt. Again, as t goes from 0 to b, as b tends to infinity. And what is going to occur in this particular case? All right, so regardless of whether we have it 0 or b, okay, for t is equal to b, okay, well, you have e to the negative b, and as b tends to infinity, okay, we have this going out to 0, and as t goes to 0, okay, this introductory term is also negligible. So the negative t to the x e to the negative t, regardless of whether the limit is at b or at 0, especially as b tends to infinity, again, the negative t to the x e to the negative t in both limits will tend to 0. So remaining, then we have this term. So you have x, and applying what we have for the limits that we can place along the integrand, we have going from 0 to b. Again, as b approaches infinity, and we have of t to the x minus 1 times e to the negative t dt. And guess what? As we go from 0 to infinity of t to the x minus 1 times e to the negative t dt, that is going to make reference to the gamma function. Again, using the frames of reference. Okay, so we have gamma of 1 is equal to 1. And we have gamma of x plus 1 is equal to x times gamma of x. So if I'm looking at gamma of 2, so looking at gamma of 1 plus 1, so I got 1 times gamma of 1. And if I go out to gamma of 3, I have the gamma of 2 plus 1. And so that would be equal to 2 times gamma of 2. For gamma of 4, I have gamma of 3 plus 1. I have 3 times gamma of 3. If we go to gamma of 5, this will be equal to gamma of 4 plus 1. This will be equal to 4 times gamma of 4. All right. So with gamma of 1 equal to 1, so 1 times 1 is equal to 1, and 2 times gamma of 2, so we have gamma of 2 is equal to 1, and gamma of 3 is going to be equal to 2. For gamma of 4, we have 3 times gamma 3, so this would be 3 times 2, which would be equal to 6. And 4 times gamma 4, we have 4 times 6, so that is equal to 24. And if you notice, okay, we're going to have in the patterns, okay, 1 is going to be 1 factorial, 2 is going to be 2 factorial, 6 is going to be 3 factorial, and 24 will be 4 factorial. So we can now say that for gamma of x plus 1, this is going to be equal to x times gamma of x, and this will be projected on out to x factorial. Now we have in Maple, instead of x, we have the input variable as n. So in the same vein, we can say we have gamma of n plus 1 is equal to n times gamma of n, and that is going to be equal to n factorial.